This meeting is being recorded.
This interactive video is going to work with one of your practice problems on hypothesis testing and z-scores. So if you want to pull out the practice sheet that has that exactly as the title at the top, practice, hypothesis testing and z-scores, and you can actually work through the problem with me. So we'll work under the second bold heading of hypothesis testing and z-score, and we'll read part of A, and then we'll move into B, because B is just changing the numbers for A. If you want to look at an example of A, look at the previous study session recording. Okay, so we have, you work for a job training and development program. You're curious about whether men or women earn different levels of income when they enter the job force. Your null hypothesis is that there's no difference in income levels between the two groups, but you're not sure which group has a greater income. You take a random sample of all your clients and get the following information. So now we're going to look down at the information in B. So we look at our first question here. Have you found a significant difference in income levels? Okay, you might be looking at this going, I don't even know how to start this. Okay, so we're going to methodically go through how to start thinking about this one. So we'll start with just transcribing our information. We know that for men, we have a mean of 11,000. That's their average income. Then for women, we have 13,000. And we have a group standard deviation. So that's when you look at all the data together. This is a standard deviation of 2,000. So when we eyeball this, you know, our initial reaction would be, wow, the mean for men is lower than it is for women. So therefore, wow, men must earn less than women. Well, we don't know that because it just could have been the way our sample was drawn. So that's why we need to test our null hypothesis that there's actually no relationship between them, and to find out how likely it is that this result that we got is due to chance, meaning just by the way we do the sample, or just due to sampling error, as opposed to this difference actually existing in the population. So because the statistical test that we've been looking at this week is a z-score, we need to start with our z-score formula. And this formula should look kind of familiar. Here it is. So we're working with the z-score, which is the same kind of test that we worked with in week 5. But now we're using a z-score to figure out to test our null hypothesis. So we find the difference between the two groups and then divide by the standard deviation. So that means we're going to be doing 13,000 minus 11,000 divided by 2,000. And then we get 2,000 divided by 2,000, which equals 1. Okay, so we've run a two-tailed 0.05 test. So let's put this on the curve and think about this here. We have our curve, and what we're saying with a two-tailed 0.05 test is that we're prepared to take a 5% chance that the results that we got are just due to the way we do our sample, which means a 5% chance that the null hypothesis is likely to be true, which also means a 95% chance that the relationship we found actually exists in the population. So we can imagine we have our null hypothesis line here. So if we're taking a 5% chance, that means we want to be 95% confident. Okay, so we're visualizing this here, right? So that means this space here needs to be 95%. So for it to be 95%, we need to have 4750 on either side. What we know from looking at our z-table, if we would look at 47.5, we're going to get a z-score of 1.96. This is our critical value. So if you recall from the lectures, it's a convention. We know that if we do a two-tailed 0.05 test, that 1.96 is our critical value. Okay, we actually know enough right now already to determine whether this is statistically significant or not. If you recall from the lecture, one of the ways that we can determine statistical significance is to compare our test statistic to our critical value. If our test statistic is greater than our critical value, we reject. If our test statistic is less than our critical value, we accept. So in this case, we're going to compare our test statistic, this is our test statistic, to our critical value. So when we make that comparison, we see that 1 is less than 1.96. So that means we have to accept our null hypothesis. And here's why. If we get a test statistic of 1, let's imagine that that falls about there. This is our acceptance region, right? This is our rejection region. And that's on both sides. This is our test statistic of 1, our test statistic of 1. This 1.96, this critical value, is the hurdle we need to get over into the rejection region. But our 1, or our test statistic, doesn't get over that hurdle. It is inside our acceptance region. Because it's inside the acceptance region, we have to accept the null hypothesis. This difference that we found between men and women, we are not confident enough that it's not due to chance. So we have to accept our null that there actually is no relationship between gender and income. Okay, that's actually the easiest way to determine significance, by comparing the test statistic to the critical value. But we can also do it with probabilities. So I'm going to clear the screen, start over, and we'll look at how we can kind of work with that curve differently and come out at the exact same answer. Okay, so we know we have our z-score of 1. And we'll draw our curve again. Okay, so we're going to set out our acceptance region right in here. So we know that this acceptance region right here is 95%, because we're still doing our two-tailed 0.05 test. We know 47.5, because this whole thing here is 95. So we know then that 2.5% is out here and 2.5% is out here, right? 2.5 plus 2.5 is 5 plus 95 is 100. So we have that set up. Now we run our test statistic and it puts us about right here. Let's say, here's 1. We'll do our test statistic. That's 1, so our z equals 1. And we know, that this is the 1.96, because we know that's a convention, and we can go to our z-table and find a 47.5. So we can actually now go to our z-table and we look for a z-score of 1. And we don't have an exact one on the table, but what we know from the normal curve is that this distance right here, this from just the general mathematical properties, is 34.13, right? So we can calculate then how big our tail is with this particular value. So we can take 50 minus 34.13, whoops, I went the wrong way. 50 minus 34.13 equals 16%. Let me get a different color here. No, that's not it. This distance here, whoops, is 15.87%. That means this distance here is 15.87%. Now what we can do is compare the probabilities. So we're going to compare, this is our rejection level, right? This is our obtained probability that we got, so we can compare them. So we would be comparing 15.87 to 2.5%. This is greater than that. Now, we usually think about it like this. We rarely think about it as percentages. So this becomes 15.87. So it's still greater than. This means that 16.16 probability that results are due to chance. We're only prepared to take a 0.025 chance that it was due to chance. So we're taking too big of a risk right here. So we have to accept. So when we look at it this way using the probabilities, it's the reverse as when we do critical value. So if you remember that if our test statistic is greater than the critical value, we reject. If the test statistic is less than the critical value, we have to accept because we didn't get over the hurdle. But if we're comparing the probabilities, it's the reverse. If our obtained probability is greater than our rejection level, we have to accept. The risk is too high. If our obtained probability is less than our rejection level, then we reject. Because we're taking even less of a risk than what we predicted. So this is going to be the key to keep in mind. When you're calculating by hand, it's often easier to do the test statistic compared to the critical value, especially when we're dealing with the conventions of a two-tailed 0.05, 0.01, something like that. But once we jump off and we're just dealing with outputs, statistical outputs from like a table that SPS prints, you're going to find that we start shifting to just being here. We're just going to compare probabilities. We're going to look at one number in a chart and go, oh, that's 0.01. That's significant at the 0.05 level because 0.01 is less than 0.05. Oh, there's a relationship. But we need to kind of work through all the conceptual stuff in the background. So, hope this helps. Dig into the other problems.